Understanding sea level variations. Hello everyone, I hope this finds you well. In this video lecture, we will discuss the subject of sea level variations. In our previous lectures, we talked about tide gauges and satellite altimetry in the context of determining a vertical reference, vertical datum, to serve as the basis of height systems. At that time, we mentioned that long-term observations from the two techniques would allow the monitoring of variations in sea level. Let us talk about monitoring of sea level variations. At the end of this video, you should have an overall understanding on why it is important to study sea level variations, on the factors that cause sea level variations, on the magnitude of sea level variations that have happened since the last glacial maximum 20,000 years ago, the signature that the last ice age left on the Earth's crust, and why it is important, methods of sea level monitoring and factors that affect them, and finally, current trend and acceleration values as derived from the analysis of the observations. Sea level variation may appear as a deceptively simple subject, but it is a complex topic of scientific interest and of increasingly considerable economic and social importance. Why do we monitor and study sea level variations? A simple answer would be for our own sake. We need to understand the place where we live, from our nearest surroundings to the whole planet, and the physical processes that govern the Earth system. And some of these processes affect our lives directly. Sea level variation has visible impacts. Sea level rise impacts erosion of beaches and bluffs, increase in flood and damage caused by storms, inundation of low-lying areas, salt intrusion into aquifers and surface waters, and causing higher water tables. Sea levels vary due to many factors. We still feel the consequences of glacial melt from the last ice age. The crust moves up and down from local to continental scales, affecting how we perceive sea level. And there are variations in water temperature and salinity. Seawater is susceptible to thermal expansion, and salinity affects water density. The balance is intricate. For example, as fresh water from small alpine-type glaciers reach the ocean, it cools and decreases salinity locally. Evaporation can also be added as a contributor. All these factors play a role and need to be considered together. For example, eustasy, which is the uniform variation in sea level happening everywhere due to the addition of water or due to its thermal expansion, is an inadequate descriptor for the glaciation event. That is because the land covered by the large ice sheets rebounded by hundreds of meters, whereas the land at their periphery subsided, in a process still happening today. Add to that the sinking of the sea floor under the weight of so much added melted water. All this redistribution of mass resulted in a change of the gravity potential, altering the geoid and henceforth the sea level. The planet has undergone climatic variations in the past without human assistance. These variations left evidence sign on glaciers, marine sediments, coral reefs, and sedimentary rocks. Air bubbles trapped in glacial ice tells 800,000 years of history, including composition of gases in atmosphere and the average global temperature. This figure shows the analysis of ice cores for the past 400,000 years. The blue and green lines indicate the temperature fluctuations in global temperature, and the red line represents the volume of ice trapped in glaciers. Please note that the vertical axis on the red line is inverted, with the lower volume of ice on the top to more clearly show the correlation among the lines. Each peak represents the short periods between the ice ages, which are represented by the valleys. In other words, ice ages are the normal. The red circle indicates where we are now, at the Holocene. This figure portrays the regions of the Earth covered by ice during the last ice age. We can see that massive ice sheets cover the southern tip of South America, Southeast Australia, New Zealand, and the northern regions of North America, Europe, and Asia. About 97% of all water on Earth is now enclosed in the oceans, with most of the rest in glaciers, mostly in Antarctica and Greenland. About 20,000 years ago, at the peak of the last ice age, there was much more water trapped in glaciers, and the sea level was about 125 meters lower than it is now. The glaciers began to melt, leading the oceans to fill, pushing the shorelines back as the sea level rose. The process decelerated to the level where we are today, indicated by the red circle. The crust has been readjusting itself from the sudden melting of all that ice, sudden in geological terms. This readjustment is expressed in both crustal uplift and subsidence. This is a phenomenon known as post-glacial rebound. The figure shows the amount of crustal uplift, red arrows, and subsidence, blue arrows, determined by GNSS. Canada, covered by that enormous ice mass, is moving up, while peripheral regions, the Maritimes, the US, and Alaska and Yukon, are moving down. This figure shows the same phenomenon in a global scale. We can see how much North America, Europe, and the southern tip of South America are still heavily affected by the last deglaciation. Therefore, our lives today are still affected by the last ice age. The two methods used to measure sea level are tide gauges and satellite altimetry. Long-term observations are necessary for the analysis of sea level variations. Tide gauges provide sea level surface relative to the land to which it is attached. Tidal records represent the situation around the tide gauge. Any crustal movement will affect measurements, and they would have to be taken into account either by the use of post-glacial rebound models or GNSS observations continuously collected at the tide gauges. Satellite altimetry provides a global perspective as it orbits the Earth, and the onboard GNSS receivers provide a global reference frame. The rate of change of sea level can be estimated from tide gauge measurements. Tide gauge measures the change of sea level relative to the crust. Measurements contain contributions from both solid Earth displacements and eostatic signals in the ocean. Tide gauge can be referenced to the Earth's center of mass using GNSS, helping to determine an absolute sea level change, eostatic, free from crustal deformations. Satellite altimetry can be used to determine absolute sea level change. Its difference from relative sea level change provides crustal deformation, example, due to GIA, glacial isostatic adjustment, or other causes. GIA is a synonym of post-glacial rebound. Both methods, tide gauges and satellite altimetry, complement each other. The factors that affect sea level measurements are continental oceanic crust uplift, downlift, dependence on post-glacial rebound models, or GNSS, but we have to realize that GNSS on tide gauges for this purpose started to be implemented in the mid-2000s. Currents, salinity, temperature and pressure, not just the sea, but also atmospheric. If one attempts to determine the sea level topography via the local response method, one needs temperature and pressure. Gravitational interaction ocean-continent, meaning difference in continental mass affects sea level, measurement and model errors, for example, electromagnetic bias, uncertainty in satellite altimetry orbit, and atmospheric refraction in satellite altimetry. This figure shows the ground tracks of Topex's Poseidon satellite altimeter over the globe for its 10-day cycle. We can see that satellite altimetry coverage is global in nature. Here we see the global network of tide gauges. Blue dots indicate the tide gauges 100 years or older. In red, the tide gauges 50 years and older, and white dots the newer tide gauges, which started operating 50 years to the present. The figure tells us that global network of tide gauges is something recent. Besides the short life of most tide gauges, there is also the fact that some of them are intermittent, which means they do not operate continuously. Nonetheless, the distribution is suboptimal as it is constrained by the shape of the continents and the location of the islands. Unlike satellite altimetry, tide gauges have limited spatial distribution, therefore providing poor spatial sampling of the open oceans. As we mentioned before, tide gauge measurements over time can be affected by crustal movements. Consider here a tide gauge measuring a mean sea level indicated by the blue line. As the time passes, mean sea level raised to the light blue line. A plot of vertical displacement over time would show a growth of mean sea level. Consider now another tide gauge. This time, the place where it is located is sinking. The sea level remains the same, but the plot of vertical displacement over time indicates once more a growth of mean sea level, this time an unrealistic growth. Scientists are very careful in quantifying whether global sea level accelerates or decelerates, which would indicate a change of velocity over time. It is a change in the linear trend. A plot of vertical displacement distance over time would be a straight line for a constant velocity. It is linear trend. If there is acceleration, the plot would be a curved line. Let us look at the tidal record of a few stations. This one is Station Juneau in Alaska, dating back to the late 1930s. It indicates the sea level decreases at a linear rate of minus 13.3 millimeters per year, with a standard deviation of 0.3 millimeters per year, with no acceleration in sight. Now, the tidal record of Station Astoria in Oregon, dating back to the 1920s. In this case, the record is flat, with a linear rate of decrease in sea level estimated to be equal to 0.2 millimeters per year. Again, no acceleration. The same now for Tidal Station The Battery in New York, New York, dating back to the late 19th century, indicating a linear increase in sea level equal to 2.9 millimeters per year. In all these tidal records, we can see a few short-term variations, but no acceleration. Also, their 1 sigma standard deviation is at the 10th of the millimeter per year. We also cannot tell if there is any land motion at the tidal stations by just looking at the tidal records. Now, tidal record from the tide gauge located in Churchill in Hudson Bay, Canada. This particular location, we know, is in the epicenter of the post-glacial rebound. Therefore, this record is heavily contaminated by the upward movement of the crust. This figure from the Permanent Service for Mean Sea Level, PSMSL, shows the linear trend of tide gauges in Europe. Blue arrows indicate negative linear trend and red arrows positive linear trend. The trends are not corrected for land movement. The tidal stations in Scandinavia, in blue, are under the uplift influence of post-glacial rebound. As you mentioned before, the peripheral areas suffer an inverse effect as subsidence. They are the remaining stations located in Europe. Therefore, it can be generalized that most tidal stations shown here are under the influence of land motion, either up or down. To account for that, one has to make use of a post-glacial rebound model or rely on GNSS-determined crustal movements, such as the reanalysis of the TIGA campaign. TIGA stands for GPS Tide Gauge Benchmark Monitoring and yields crustal motion in a global reference frame. The problem is that the idea of placing GNSS receivers continuously operating in tidal stations started to be put in place just about 15 years ago. Therefore, the time series of GNSS values is very short. A paper written by Vrejeva et al. In 2014, the latest referenced by the PSMSL, estimated trends and acceleration of global and regional sea levels since 1807. Their results, referred to as reconstruction, suggests a linear trend of 1.9 plus or minus 0.3 millimeters per year during the 20th century, with a 1.8 plus or minus 0.5 millimeters per year since 1970. Regional linear trends for 14 ocean basins since 1970 show the fastest sea level rise for the Antarctica. This is the linear trend, 4.1 plus or minus 0.8 millimeters per year, and the Arctic linear trend of 3.6 plus or minus 0.3 millimeters per year. They calculated an acceleration of 0.02 plus or minus 0.01 millimeters per year squared in global sea level from 1807 until 2009. Now, let us look at what satellite altimetry says. This plot shows the time series of mean sea level anomaly starting in 1993, ending in 2019. This is still a relatively speaking short period, only 25 years, but it provides a global perspective of the most recent sea level rise. The linear trend is 3.1 plus or minus 0.4 millimeters per year. There are periods of slow and fast sea level rise associated with the decadal variability, something reported by several authors. The longer the time series, the better to avoid biases and misinterpretations. A recent paper from the groups at NASA and University of Colorado, led by Hamilton, investigated the acceleration of sea level rise estimated from satellite altimetric data. The key points in their judicious work is that after removing all potential errors and biases, they could not detect neither acceleration nor deceleration. A longer time series is necessary. This is figure 3 of the paper showing linear trends and acceleration. Let us concentrate on the bottom maps, the residual solution after removing two modes of internal variability. The bottom left map shows the linear trends. Look at the scale. It goes from no trend, white color, then growing to the maximum estimated trend of 6 millimeters per year in deep red. The trend is not the same everywhere and vary with location. It is interesting to notice that the largest trends are in deep ocean away from most continents, with the exception around the Filipino archipelago. A visual inspection suggests that the trends at the seashore get closer to the ones estimated from tidal records. The bottom right map shows the accelerations. Most of the area shaded in gray represents estimates that are not statistically significant, that is, most of the oceans. One cannot tell if there is acceleration or deceleration. Our take-home message is as follows. Number 1, geodetic techniques, tidal records, GNSS, and satellite altimetry are of fundamental importance for the monitoring of sea level variations. Number 2, linear trends and acceleration, as estimated by different techniques, are tide gauges, 1.9 plus or minus 0.3 millimeters per year during the 20th century, 1.8 plus or minus 0.5 millimeters per year since 1970. There are regional variations in trend. Acceleration 0.02 plus or minus 0.01 millimeters per year in global sea level, estimated from 1807 and 2009 records. Satellite altimetry, 3.1 plus or minus 0.5 millimeters per year since 1993. There are regional variations in trend, and acceleration is not statistically significant. These values yield a global sea level rise between 14 and 25 centimeters by the year 2100. It is a big mistake to blend the results from the two techniques to claim that satellite altimetry indicates acceleration in sea level, when each technique independently cannot detect any. It is fundamental to realize that tide gauges and satellite altimetry capture different spatial information, and their estimates represent different phases of the same phenomenon. Much analysis is required to determine a global sea level rise that can be used scientifically with confidence.